In this training video, we're going to start off with a little review on intervals, move on to something new that can help you find some cardiac disease, including NMI, and we'll study axes and QRS transitions. The intervals we're going to measure today, the intervals we are going to review today, are the PR interval, the QRS interval, the QT interval, and the R to R interval. So taking a look at the PR interval, the PR interval measures the time from the beginning of atrial depolarization to the beginning of ventricular depolarization. And to measure the PR interval, what you're going to do is find the most visible P wave on your 12 lead printout, and then you're going to measure from the beginning of the P wave to the beginning of the QRS complex. So just to review, to measure a PR interval, a normal PR interval is between 0.12 and zero point 0.2 seconds, or which would be 3 to 5 small boxes on your EKG printout. You can see right here in this printout, it's 1, 2, 3, 4 boxes. So this is a normal PR interval. A PR interval greater than 0.2 seconds is called a prolonged PR interval. Commonly, this is due to an increased AV conduction delay, or this is seen as a first-degree AV block. And of course, a PR interval less than 0.2 seconds is called a shortened PR interval, and this is common in patients with Wolff-Parkinson's-White disease. The QT interval measures the start of ventricular depolarization to the complete ventricular repolarization. If you look over here, you can see the QT interval is starting to be measured right at the first Q wave and all the way to the end of the T wave. And a good visual test to quickly measure for a normal QT interval is to check to see if the QT interval is less than 1/2 of the R to R interval. And we can look right here at our picture. So the R to R interval is from the peak of each R wave apart. So we see the R to R interval here is 22 small boxes, while the QT interval is 10 small boxes. So this is a normal QT interval because it is half of the R to R interval. So some other stuff about the QT interval is the QT interval will shorten with a faster heart rate, and the QT interval will lengthen with a slower heart rate. But what is the QT interval? What is it telling us? What is the QT interval revealing to us? So we know a prolonged QT interval is associated with an increased risk to ventricular arrhythmias, especially torsades de pointes, which is potentially a fatal arrhythmia. A prolonged QT interval can also be due to an electrolyte abnormality, such as hypokalemia, low magnesium, low calcium, hypothermia, and maybe even an MI. So I'm going to give you a little spoiler alert before we begin this, just to let you know why we're going to go over QRS access. So an abnormal QRS access can actually reveal some sort of cardiac disease, including a heart attack and its location. So the QRS axis is much easier to understand than it may look here, especially in this picture. Simply, the QRS axis is just the mean or the average direction of depolarization in the frontal plane. A normal QRS axis is from positive 9 degrees to negative 30 degrees. So if you look right over here at this picture, what we mean is a normal QRS axis will be between AVF and all the way up to AVL, which is negative 30 degrees. So you hope to find this QRS axis somewhere in this shaded blue area. When the QRS axis is between negative 30 degrees and negative 90 degrees, it is called left axis deviation, or LAD. So one cause of LAD could be an acute or old inferior MI. Another cause could be, or another cause of many, could be LVH. So if you look up here to our diagram again, so if you notice that the QRS axis is in between negative 30 AVL and all the way up here to negative 90, that could actually reveal an acute or old MI or some other related cardiac disease. When the QRS axis is between positive 90 degrees and 180 degrees, it is called right axis deviation, or RAD. And in RAD, if the cardiac deviation is in right axis deviation, the patient may be having an MI in the lateral leads. Another cause could be RVH. And then a lot of times, tall and thin patients with COPD will have right axis cardiac deviation. So I know what you're thinking right now is how do we find the mean or the average direction of depolarization in the frontal plane, or how do we find the QRS axis? There's definitely one way to do it that's not too hard by looking at this diagram, but luckily for us, there is also a much easier way to do it. So if you do want to look for the axis deviation, the QRS axis deviation, all you have to do is look at your 12 lead printout, and you can see right here where it says PQRS and then T axis, and then go here to the corresponding area where you'll see 45 degrees, 50 degrees, and 49 degrees. So this patient right now has 50 degrees of QRS axis, so they are in the normal range. Some are right around this area. But really quickly, if you do want to know how to do it without just looking at the printout, it's actually pretty easy to do. So if you take a look at your 12 lead here, we don't have all our leads, but we have a lot of them. And as you know, uh, as the electricity move towards a lead, then you're going to see a upward or a positive deflection. As the electricity moves away from that lead, you're going to see a negative deflection, which is also going to be important in the next section of this video. But if you think about it, if you're looking directly at it, you're going to see a huge positive deflection. If you're looking directly away from the axis, you're going to see a big negative deflection. But if you're looking at 90 degrees from it, it'll be pretty equal, both negative and positive. So we can actually see that right here in AVL. So then we'd bring it over here. We look at AVL, but we know as we look at AVL, we know we're looking at 90 degrees from AVL. So what do? We look down at 60 degrees. So that gets us pretty close. There's ways to fine tune it, um, but I don't want to get into that right now. So it gets you pretty close. You know, you see, you think this lead 2 right here is 90 degrees. So you would say this is about 60 degrees cardiac axis deviation without having to print out. And just really quickly, why it's important to know where your QRS axis deviation is because remember, if you have a deviation, so if this number is in between negative 30 and negative 90, your patient actually might be having an inferior wall MI. And if you see a QRS deviation between 90 and 180, um, maybe an MI in the lateral leads. So the next thing we're going to talk about is a QRS transition. As you see here, we zoomed in on the V1 through V6 on a 12 lead printout. And so as you're looking at this, the QRS complexes should go from a negative complex to a positive complex as you move from V1 to V6. Um, so if you think right here, this black line is your isometric line. As you can see right here, this QRS, anything below the isometric line is a negative deflection, and then anything above the isometric line is a positive deflection. You can expect to see the QRS transition move from positive to negative in the V3, V4 area. So that's exactly what happens here. So if you look at V2, this is our positive deflection, and this is our negative deflection. And I actually took this positive deflection and measured it against the negative deflection. You can see the negative deflection is actually larger than the positive, so this is still a negative, net negative QRS complex. But here, clearly in V3, it becomes a positive QRS complex. And you can see here's the negative deflection measured against the positive QRS. So in this QRS transition, we would say it changes to positive V3, which is normal. So this is just simply called a normal QRS transition. Another terminology or something that's very similar to the QRS transition is R-wave, R-wave progression. So I hope by now you recognize we're not just going over stuff just to go over stuff. There's actually something to be gained by knowing the QRS axis. It can actually reveal an MI. The same thing is true about QRS transitions or an R-wave progression. Is it actually can reveal some cardiac disease. Namely, can reveal an MI. So if you look over here, we have an early and a late QRS transition. First thing we're going to go over is the early transition, what the problems with an early transition might be. So an early QRS transition or a QRS complex positive before V3 might be a sign of a right bundle branch block, and some other problems might be RVH or even a posterior MI. So how do we know it's early? If you look in here, so remember it's supposed to become positive in V3 or V4. And you can see right here the QRS complex. I took the negative deflection and measured it against the positive QRS, and you can see the positive is actually quite a bit bigger than the negative deflection. So it's already a positive deflection in V2, so that means it is a early QRS transition. And then you take a look over here at the late QRS transition, where it becomes positive after V4. So again, I measured here. If you see the negative QRS is taken against the positive QRS, and it is still negative in V4. Um, V5, it looks pretty neutral. You might have to take the area under the QRS to figure that out. But what a late QRS transition or late R wave progression might reveal is an anterior right ventricular or septal wall MI. But again, you can't differentiate just by looking at this if it's an acute or an old MI. And then maybe a little less important than figuring out if it's an MI is it might reveal LVH. So luckily this is the end. What I would like, if you get a 12 lead you're unsure of, or just an odd or weird 12 lead that you don't know how to read it, go ahead and send me an email, and we'll see if we can get an expert's opinion on your 12 lead and try to figure out what was going on with your patient. All right, thank you.